let's start problem solution from previous chapters, the chapters that are going to be in the exam. So, chapters 25 through 28. Okay? Okay. These are mostly previous exam questions. Maybe you have already solved some of them, but please don't hesitate to ask questions. Some of them are easy, some of them are hard. Okay, let's see what this problem is asking. So this is RC and there's a voltmeter. Okay. A voltmeter of internal resistance R. So voltmeter itself has an internal resistance of R. Is used to measure the voltage across the capacitor after the switch S is closed at t equals to 0. So at t equals to 0, this one switches is closed. Okay, because the meter has finite resistance, part of the current supplied by the battery passes through the meter. Given that the capacitor is uncharged at t equals to 0, what is the reading of the voltmeter at t equals to 0? Any ideas? Did you follow the question? So at t equals to 0, we close this one, and at t equals to 0, Q t equals to 0 is 0. So what is the voltage at t equals to 0? 0. Very easy, 5 points. Okay? Since charge is 0, and since voltmeter is going to basically calculate, I think I figured out. Okay, this is the way to, show something in this updated version. So, across this, so voltmeter is measuring voltage across this, and Q is 0, voltage is 0. That is the answer of part A. Okay, part A, V at t equals to 0 is 0. Part B, what is the reading of the voltmeter at t equals to infinity? Do you understand the question? 0 again. Why?
Because there will be
so maybe I should really plot this inside the voltmeter, like the very inside of the voltmeter it has an internal resistance. So what it is calculating, what it's going to show is the potential difference between these 2 points. Okay? Come on. Batteries live forever, don't you know that?
Oh, okay.
We already discussed this. Of course, at infinity, normal batteries are dead. But when we ask what happens at infinity, we mean after 10 times the time constant. Yes? So it's either filled up. So in this particular case, after enough time, capacitor is filled up, right? So what does it mean for the capacitor? It means that at t equals to 0, at t equals to infinity, as t goes to infinity, the current here is going to be 0. Now why is that? It will be fully charged. All current will flow instead from here. So IC will be 0, but I in the circuit will flow like this. And we can just write I times big R plus small r, right, equals to E. Then I is E over R plus small r. And the voltmeter is reading what? E times E? You mean I, right?
Yes.
Small r. So it's going to read E times small r divided by R plus R. Everybody agrees with this? Any questions? No?
At what point we are going to charge the battery? Capacitor is going to charge the battery, right? At some point.
No, why it should?
But I think it should oscillate, maybe.
Okay. It won't oscillate because it's a first order system right now. We don't have L,
Okay.
okay? So we don't have inertia, right? There's nothing here that wants the current to persist. That's why it's not going to go over to the other side. It's not going to overcharge so that it comes back, okay? Very good question though. So part C, any other questions? Yes.
Işıkta benim hep şeyde kafam karışıyor. Hani tam T equals zero'da kapatıyoruz ya. Ama uncharged sağ, o yüzden volta farkına 0 diyoruz. Ama tam kapattığımızda sonuçta bir şey geçmiş olacak. Yani
Don't worry about that. It's exactly t equals to 0 and not even Planck time passes, okay? The whole universe stops working, just t equals to 0, okay? Any other questions? Yes.
Hocam, if we assume that at the beginning there is a charge in the capacitor, and there will be a current, right, at t equals 0.
Sorry, I was distracted by Galatasaray and was playing a song in my mind. Can you repeat?
If we assume that at t equals 0 there is a capacitance, there is a charge on the capacitor, then can we say that there is a current passes through that capacitor at t equals 0?
Are you asking what would be the solution if there was a some charge
Yes.
on the capacitor? Yes, we can solve that. We also need, in this case, which way it is charged. Is it charged the right way or the wrong way? So yes, eventually, let me do the last part and then come back to your question, okay? The last part asks what is the reading of the voltmeter at any arbitrary time, okay? We know what it is at t equals to 0, it's 0. At t equals to infinity, it's this one. And we actually can guess what's going to happen. Don't do this in the exam, but I am guessing that okay, no, it's not that obvious. So here's the thing. This is a good guess. Like eventually it has to go here, R plus R, and it has to go like this, right? 1 minus e to the minus t over tau. But what is that tau? It's not. So you are claiming that tau is R times C, right? But it is not because of this one. Okay? Because of that one, yes. So the system has yet another R, but then the question is how that R gets introduced here. Is it simply this? Is it simply this? Meaning that they act as if they are in series, okay? Or is it this?
It depends on the capacity. It's charged or
It depends how it is connected, okay? And it is connected in such a way that this is the answer. But let's do it all the way. Let's do it all the way, okay? So I will erase this. I will erase the whole thing here. Or maybe I can shrink it and leave it here. Then we will erase it. So at any arbitrary time, to figure it out, you need to properly draw this circuit one more time. You have small r's here, a C here, and an E here, and this is the system, right? Then you have to write down Kirchhoff's rules. Okay? You have a question.
Why we take that R to the side?
Doesn't matter. Do you think it will matter if this R is not there, but here? Does it matter? No, it doesn't, right? Yes.
I thought the logic on the voltmeter was the resistance is so large so that no.
Exactly. That's why the question says that because the meter has finite resistance. You see? Yeah.
But wouldn't that cause the voltmeter wouldn't work?
No, it will be calibrated accordingly. Okay, all voltmeters have resistances anyways, right? And they are calibrated accordingly so that they hopefully measure the right thing. Any other questions? Yes?
No, in this case, is capacitor fully charged or not?
In this case, it is at any time t where this is neither fully nor empty, neither full nor empty.
But if it's charged, then
If-
I think resistors will act like they're connected in series because there will be no.
Yes, that's what we did here. That's what we did in part B. Do you see in part B? Do you see it or not? In part B, we have ignored this part. That's why we got them in series.
So it depends on
It depends on.
capacitor.
Is that what you were saying before? Were you saying that it depends on the capacitor? Okay, now I understand what you were saying. Because otherwise, I couldn't get it. But now I get it. Yeah. Okay. Q. And let's. Okay.
John, there are two loops.
Yes, there are two loops. Yes.
So which one are we going to?
Both. You have to deal with both. You are not happy.
No, I was confused because so for the total current is IR and the IC.
Mm-hmm. Yes, like you start with this equation.
And leave it alone.
Then we continue. We know that IC is dq over dt, right? What else do we know?
C is equal to QT over VT. And
Yes, Q over C is equal to IR times R. Do you agree with that? And finally, E is IRR plus I big R, big R. I didn't do it in the Kirchhoff's way, but you get it, right? Do you have any questions? So if you rewrite it properly, then you get this equation, dq over dt, which is IC, plus q over RC, which is IR, small r, times big R, which gives you I big R, is plus q over C is equal to E. So I do the same trick. What do? I multiply it with RC over R plus R. And what do I get? I'm doing it a bit fast because, okay, maybe let me give you one more step. I will multiply over here. Okay, one more step. What is that step? I'm just collecting q's together. Okay, dq over dt times r plus q over c, r plus r over r. Do you see why I multiply with this now? Because I want to leave q alone, just like I did before. What do I get? I get RCE over R plus R equals dq over dt. Please let me know if you are not following, because I'm just using my notes. And eventually we come to this part. That's why I told you that we should solve it this way. Then I will answer your question. What was your name? Sorry. Onat. Onat, now comes your question. And we will answer that question now. Do you remember your question?
Yes.
What was it?
What if the capacitor have charge initially?
Exactly. If it has charge initially, then you don't integrate from 0. You integrate from q initial to any q. That's it. That's the only difference, okay? From 0 to t. Let me just write it as q0. Okay?
Don't have any charge at the beginning.
Yes, but he asked, what if I have some charge at the beginning?
Just for the symbol, we write Q.
Yes, let's write 0 because I have answered your question, right? Now it's 0, and this is what you get. What voltmeter reads is Q over C, which is what we guessed earlier. E times R over R plus R, and 1 minus e to the minus R plus R t over RRC. This is what it reads. Any questions? Yes.
Hocam, if the equation of current is asked, then we take the derivative of this, right?
If the yes, exactly. So let's just write it down. But that will be which current? That will be IC. Okay. If you want IR, then you have to do a bit more steps. But otherwise, yes, this is it. So let me just write IC of t is just the derivative of this one, which will give me E times R times C over R plus R e to the minus, let me just write T over tau, and you know what tau is. Tau is RRC over R plus R. Sure. Any other questions? Comments? Suggestions? Ideas? We guessed according to, so we know that it's a first order differential equation, and we know that there are no oscillations in first order differential equations. So our guess was based on this. The previous part of the question, okay, we found that at 0 it was 0, right? And at t equals to infinity, it was some v0. And v0 was ER over R plus R. We knew that it had to approach it asymptotically. One moment. So that was our guess, but our guess didn't include tau. I mean, we could see that it must be v0 times 1 minus e to the minus t over tau, but what was tau?
I get the tau part.
You get the tau part from solving it properly. Yes, Ali?
It's the dimensions of the current equation, correct? Like, tau'yu aşağı indiremedik orada.
Yes, something is wrong here. So let's see.
Tau'yu hesaba katmak.
Yes, that's right. So what do you get if you include tau? E over R? I erased too much, so let me just... Do I get E over big R?
Yes.
Yes?
And then minus.
No, the minus takes out this
Yes,
minus.
true.
Very good observation, and again, as you have mentioned earlier, to tell people that you should check units and don't do this kind of mistakes. Sure.
So we found the what will demonstrate the voltmeter, right?
Mm-hmm.
That way. But in that case, voltmeter has some current through it.
Yes.
So doesn't it change? Like it will also measure that part, the resistance part. Why
Yeah.
didn't we include that?
In general, voltmeters report to you the voltage across its edges.
Yes.
Okay, over between this point and this point. Okay, so it includes that effect of having a certain internal resistance. That effect is included. Okay, do you remember? Maybe you can briefly look at our design of the voltmeter, what we had there. Should we? Okay, let me check whether we can actually search here voltmeter. Do you see? Brilliant. It actually reads my handwriting. Do you see the design here? So it already takes into account the fact that voltmeter has some internal resistance. Okay? Yes, tell me.
Isn't the no what circuit element between the points A and B, can we really not in this problem?
Mm-hmm.
The drawing of the voltmeter.
Oh, yes, I realize there is some problem there, but I just didn't draw something.
There is no circuit.
Yes, yes.
A and B will have the same potential.
Yes, so that particular voltmeter will read 0. Okay? Some people find some stuff funny, some people don't find that stuff funny. In this particular case, I found it funny and laughed. All right. Should we move on to the next question? Yes? The next question, oh, it will be erased. Okay, the next question is this one. A long straight wire carries a current I, and it's very long, like this. So basically, it's semi-infinite in this direction, goes to infinity. In this direction, goes to infinity. Over here, let me actually draw it like this. Over here, it has a curve. And the radius of that curve is r. Do you understand the question? The geometry? And there is some current running through it. And that current is I. Okay? Can you guess the question? What is the magnetic field over here? Okay? How would you solve this problem? Divide into 3 parts. Very good. So let's start with this part over here. That's a semi-infinite wire. You could use integral, okay, or you could use Ampere's law, but be careful. Like, you can only use Ampere's law here because of certain kind of symmetry here. So you can use Ampere's law for infinite wire indeed, which is infinite in both directions. But here you are using yet another symmetry. You are using the fact that if infinite has, let's say, magnetic field B, then semi-infinite, which is not going to infinity on one side, should have the same magnetic field divided by 2. Do you understand this? No. Okay, let me explain again. So infinite wire going infinity in both directions. How do we find the magnetic field at a distance r? We just say B times 2 pi r is equal to mu 0 I. And we say that B is equal to mu 0 I over 2 pi r. So far so good? But if you have semi-infinite wire, then you just say that, okay, this is half of the infinite wire, so B must be half of the total B. That's what we are doing here. Okay? Then, because of this purple wire, you have a B of V going in, and the amount of B is because of the purple part is mu 0 I over 4 pi r, big R in this case. Okay? Going in because if you put your thumb like this in the direction of the current, then magnetic field goes in. Okay? How about the rest of the wire where it is over here? Is it in the same direction?
Yes.
It is. Is it semi-infinite? Yes. Same thing. So it turns out that these two actually do account for the same magnetic field after all, which is B0 I mu 0 I over 2 pi r in total. How about this section over here, this green section over here? That needs to be solved separately. So for the green section, we need to use Biot-Savart, right? So let me write it down. Let me draw it again over here. So dl is always perpendicular, right, to this r unit vector. So we will have dB equals to mu 0 over 4 pi I dl cross r unit vector divided by r squared, which is big R squared, right? And the total magnetic field coming from this is going to be mu 0 I over 4 pi r squared times the length L, because it's always perpendicular, always you get dl. You simply have an integral of dl, which is L. And what is that L? What is it? Pi r over 2, because it's a quarter circle. So the magnetic field due to this one is mu 0 I over 8 r. Okay? What is the total magnetic field? B total is, this one is also inwards, right? Oops. This one is also in, because if you put your right hand like this, goes in. Everything goes in, so B total is going in, and the value is mu 0 I over 2 pi r plus mu 0 I over 8 r. Okay? Yes.
I'm always confused about the L cross product R. Is there any like easy way to find it out? This is easy for this question, but like in some cases, in line maybe.
It's, I don't know what to say really, because dl is the direction of I, okay, and r unit vector is starting from the wire towards the point where you want to find it, and you just write down sine of the angle in between.
And the magnitude of L and R?
And the magnitude of just dl.
Why
The
not R?
R unit vector.
Oh, sure.
R is the unit vector, okay?
Now it's making sense.
Thank you. Any other questions? No?
Is it all the time sine theta?
Sine theta. Sine theta of dl and r, because it's cross product. So it could be this kind of angle. So maybe that angle is not good for you. Maybe you are using sine of this one, which is fine. I think sine theta was equal to sine pi minus theta. So you can use this theta on the other side if you want.
Yeah, what about the sine of dl cross r?
Sine of dl cross.
It can be minus, right? Since it's a vector.
Yes, of course, it can be minus.
So but it's ever like this.
It's always plus, right? Let me see why. So for it to be negative, it must be larger than pi. Okay, and that never happens. Why is that?
It can be.
Can it be? Yes, it can be. Okay, let's imagine a case where it's larger than pi. Let's at least try. So this is dl. If I choose a point here, then it's pointing here. It's less than 180. If I choose a point here, then it's pointing there. Then it's less than 180. So it's always less than 180 because your r is always in the same direction.
To the center. Yeah. Otherwise, we don't have magnetic field.
No, I mean,
If that point was on the wires,
you know, you never write the cross product with this angle, right? You always use the smaller angle. That's basically what it is. Let's say you have two vectors like this. You never think about that angle, right? You always think about this angle. Okay, and in this particular case, it's never these vectors. Okay? Good.
Hocam, also R's direction always towards the center.
Yes. Towards the point where of interest. Point of interest. Point where you want to find the magnetic field. So let's continue with yet another problem, yet another question. Let me write down here. So in this case, I have a wire like this. This is the first wire and it's carrying a current of I1. And then there is a second wire that goes like this. Do you understand the geometry? And for this wire, current is I2. All right. This radius is R. And let's see.
is it like
Yes, a half of a cylinder, but it's not a surface. It's just a wire. Okay. Half of a cylinder would be interesting. The axis of the loop coincides with the wire. Calculate the magnetic force exerted on the loop. Okay? You understand the question, right? So let's start with the following question. Which force is easier to calculate?
Parallel cycling.
Hmm?
Parallel cycling. Parallel. Straight.
Okay, parallel one is easier to calculate, but my question was rather whether it's easier to calculate force on this one because of this one or force on this one because of this one. Which one is easier?
Second one is also.
Second one, because?
Düz olmalı.
Yes. Because this one is straight and we know how to calculate magnetic field for that one. Although we do know how to calculate magnetic field for this one, it will be very complicated. Right? Way more complicated than the other one. So, let's calculate the force on these sides first. Okay? How would you calculate them? So this current is generating magnetic field in this direction, right? But notice that that direction is opposite to I2. So what will we get from dl cross B? 0. Did you follow this?
Which one's magnetic field
Okay.
is that?
Okay. The magnetic field due to the blue wire looks like this. Okay. While the current I2 is running opposite to it. This I2 is running opposite to it. Right? Excuse me. Thank you very much. Hence, it's 0, right? The angle between them is pi, and sine pi is 0. How about the bottom one? 0 again, very good. But this time the current is actually in the same direction. But 0 again, because sine 0 is 0 as well. Very good. So we are only actually interested in these two wires. All right. For this one, the magnetic field is like this. And which way is the force? Right. In this direction. Right? And it will be basically B1 times, let's give it a height h. B1 times I2 times h. What is B1? At a distance r. Mu 0 I1 over 2 pi r. Do you agree? So F, let me call it F right. Or should I call it? Yes, F right, on the right part of the wire, is mu 0 I1 I2 h over 2 pi r. How about the left part? For the left part, the magnetic field is going this way and the current is flowing up. Which way is dl cross r? Sorry, dl cross B. What do you mean by into the page? Do you mean this way? In the same direction as FR, right? Don't you agree? So FL is also equal to this one. As a result, F total is twice of this one. So mu 0 I1 I2 h over pi r. Right? Everyone is happy?
Why did we take B cross DL?
Did we take the B cross DL?
Because
We
you said sine, I mean, we consider the
sign of
sine of like B take the cross product of
Yeah.
that. That's why it's 0, right?
yes,
Sine phi is.
yes.
Why did we take the cross product of B and DL?
Why we shouldn't? Because the law is like that. F is I dl cross B.
Well, I thought Ampere's law and
What did you
Ampere's law and this was
Okay,
product
so
and-
something mixed up.
yeah.
Hocam, may I ask a question? For the first magnetic field direction, did we found correct? Because I confused, like, I think it's into
Put your thumb up.
To the for the first one is B. The şey.
Which way are so?
B ile şöyle yapmayayım. B ile koydum. B.
Wait. What? B ile B I L. No, you are confused.
Aydan Bey.
Ha, şöyle yapacağım.
Ee,
Tamam. Pardon ben cross'u yanlış aldım. Özür dilerim.
Okay. No worries. But the thing is that you are doing something different. So you put your thumb up like together with I1. So magnetic field just rotates like this.
For the first one. I was listening.
Yes, for the first one. For the force.
First one.
For the force, you do dl cross B.
Ben tam tersini yaptım.
Yes. So it's L cross B or I cross B. Any other questions? No? Good. Let's have a break.